So welcome back to the channel. Today we're going to be having a mild introduction to media mix modeling, a gentle introduction of what it is and how it works. Let's first start with what is media mix modeling. Media mix modeling is a statistical analysis technique to help marketeers understand their media mix and optimize their media mix. Media mix modeling is a privacy friendly way of measuring your media impact and to attempt to do optimal budget allocation. Marketeers need a way to plan where to spend their media dollars and where that spend is more effective. And media mix modeling is one of the ways that they can achieve that. Now, how does it work? One is collecting historical data on sales, historical data on your marketing efforts, your exposure metrics, external factors, and you're trying to do a regression model such that you can account for the direct marketing effects and the indirect factors. When we're talking indirect factors, we're talking about economic conditions, seasonality, competition, market changes, and other. And we want to use regression analysis to evaluate the ad stock effect of one's media, i.e., the delayed impact of it, and the saturation effects, also known as the diminishing returns. And we want to do this while accounting for all of the channel interactions. So, bottom line, we're trying to do a form of attribution. We're trying to quantify how much each marketing channel is contributing towards sales. And by having this attribution, we can then optimize and use those insights to guide us into optimal budget allocation. So there's basically two types of, and there's open source and private vendors, but mostly they fall into two buckets. Either they are frequentist or they are Bayesian. The difference is a little bit on the school of statistics that we're using. For instance, Meta's Robin is a frequentist and Google's Meridian is a Bayesian. So what is the difference? The first one is based on classical statistics. You're using fixed parameters, you're provided with point estimates. It is generally simpler to implement and generally it is less computational intensive. The reason for it is that Bayesian MMMs require Monte Carlo sampling, frequentist MMMs don't. Now, there are some issues. For instance, variable collinearity is a common issue in frequentist MMMs, and you need a way to deal with this. The way, for instance, Meta deals with this in Robin is by using a ridge regression. Bayesian MMMs, on the other side, Bayesian allow the modeler to incorporate prior knowledge, to incorporate business insights, such that you can try to guide the model towards what you believe is reality. Bayesian MMMs are way more computational intensive. They are way more flexible in their modeling. They are better at handling small data sets. The difference is also in the output. So while frequentist MMMs provide you with point estimates, Bayesian MMMs will provide you with distributions, and then you can do uncertainty estimations. So a common question is, what data do we need and how much? So the current guidelines, both from Google and Meta and others, is you need at least 2 years of weekly data. If you're using monthly data, you need 4 to 5 years. Generally, rule of thumb, you need a minimum of 10 to 20 observations per feature. And when we're talking feature, we're talking variables, a channel, seasonality, an economic factor, a competition factor. And this is a limitation of a regression model. You can think about it like this. If you have 100 data points and 10 features, on average, each one of those features is going to use 10 data points. This isn't strictly mathematically true, but you can think about it this way. Now, you need media data and non-media data. On the non-media data, you're thinking of historical patterns, you're thinking of holiday periods, you're thinking about some promotions that you did, you're thinking about macroeconomic variables like inflation or unemployment, and you're thinking about competitor activities. On the media spends, on the media activity side of thing, you need your actual spend data, and this is very important. It needs to be your actual spend data, not your planned spend data. Your needs to be built on what actually happened, not what you thought should have happened. Also very important is you need an exposure variable. You need impressions for digital channels or GRPs for TV, but you need a variable that will tell you how many potential people got exposed to your marketing activity. And this is very important. You should use the exposure metrics to do the media mix model. You should not use the spend data. The spend data is used after for optimal budget allocation, but the actual model is built on this exposure data. You should have this for both paid and organic channels. And this is a common issue. If you're modeling paid search, you should also have organic search. For instance, there is a common bias when modeling paid search where you need the interactions from organic search. And so you need those organic metrics. You need, for instance, Google's query volume to correctly attribute and model paid search. And you should have as many campaign attributes as possible. Usually, the recommendation is you should go until tactic level. So, if you're running brand campaigns and generic campaigns or awareness, you should model them. But be careful due to the data point requirement, you can't go very granular. So, you could go campaign, but for instance, in paid search, you cannot go towards keywords level data. And on the data quality side of things, we need a couple of things. First is consistent measurement. Second is minimal missing values, but way more important, and that's why it's on the top. You need an adequate volume of activity and sufficient variation in the variables. And this part is really important and often is missed. A regression model can predict and evaluate the relationship between variables if there is variation in them. Because you can think of a regression model trying to understand which channels are moving your sales when. There is variation in your data, another issue. If all of your channels are moving in sync, when paid search goes up, paid social goes up, and vice versa, then there is zero information for the model to extract. So variability is important. Now, there are this is an introductory this is an introduction. So we're not going to build a full. Let me know in the comments below if you want a video about the actual implementation in Python of a simple toy. But there are several building blocks we need to build, and one of them is ad stock. So, what is ad stock? Marketing activities have lasting effects beyond the period in which you spent. So, think about it like this: when you do an ad on TV, people will remember that ad long after that ad was shown to them. And the goal of some marketing, in this case branding, is to get your brand inside of your potential customers, and customers The objective of some type of advertisement is to get the brand inside of your mind so that when you are deciding to purchase, it just pops up that, oh, I want that brand. So some media has long exposure times, other media has really short. And a very good example of short ad stock or a very short lasting effect is paid search. You usually don't remember the last paid search ad you saw. But when you're searching, there's a high degree of intent. And if you see an ad that is correlated with what you're searching, you will click it and you will convert. So paid search traditionally has way shorter ad stock. So in general, we can think of it, the higher in the funnel you are, the longer the ad stock. Some channels, this is not true. It depends. There's modeling involved, but this is a general rule of thumb. So you're doing this because you need to measure the carryover and the decay effects of your media spend in the model. In this regard, MMMs are lagged variable models in which you're trying to, say, account for I spent X amount of dollars and got X amount of exposure on a specific ad, but then I got 50% of that effect on the next period and 20% on the period after, and so forth. There are ways of implementing this. Most models use one of two types. Either you have the simplest form, which is geometric ad stock, which is basically exponential decay. The second, which is way more flexible, but it's computationally more intensive, is the variable ad stock, which is basically a probability. It's basically a probability distribution. It's better for digital media. It's, for instance, it's what Robin uses underneath by Meta, but it is slower and more computational to get to it. And you want to get to account for delayed responses and advertising wear-out. After ad stock, there is the saturation. And in here, it's another very important concept, which is marketing effectiveness isn't linear. I There will come a point in which you will have diminishing returns. It's not just if my campaign is effective at 100,000 spent, I will throw a million, 10 million, I will always get the same thing. Good example of this is, for instance, paid search, where if you're at 20% impression share, then an increase in the budget will get you far. But if you're at 99% impression share, i.e., you're getting 99% of the impressions you are qualified for, then spending more will not get you one for one. The easiest way to think about this is with this chart, where there will initially, when you spend, there's the ramping up phase where you're going to get more out of your dollars of media spend. Then there's going to be an optimal range, and there will be a point of overinvestment. And the question is, how can we model this? And MMMs usually have one of two models. Either you have the logistics function, which is basically an S-shaped function, and that's the mathematical formula for it. And the second model, which is way more flexible than the first, is the hill function. And the hill function, you can model both S-shape and C-shape. And most marketing tends to be C-shaped curves, not S-shaped. But basically, you have that flexibility. And now comes the question, when applying ad stock and saturation, what comes first? And order matters, these functions are not commutative. Different sequences will produce different results, and this can affect model accuracy. There's a bit of a rule of thumb, and you need to test, but the rule of thumb is apply ad stock first when the spend in each period is small compared with the entire spend. Media activity is continuous, you have a gradual build up phase, and your campaigns have a consistent spending pattern. apply saturation first when your spend is concentrated in very few periods. You have a bit of a non-off pattern and you have high spend intensity in short bursts. Generally, most advertisers will be on case one. So usually you apply ad stock first and saturation next. But the order matters. Now, going back to a point I mentioned earlier, impressions versus spend. When you're doing the model, you should use an exposure metric. So you're talking GRPs for TV, gross rating points, you're talking impressions for digital advertising. You want to know how many people got exposed to my ads. Because spend is a very imperfect metric for that. Due to ad stock, due to saturation effects, spending more doesn't always mean having more exposure to more people. But the objective of one of them is to achieve optimal budget allocation. I want to understand where should I put my money. So we need a way to relate impressions to spend. And the usual way you do this is using the Michaelis-Menten function, where you're basically modeling the relationship between advertising spend and the exposure. The function is you're trying to fit Vmax times spend divided by Km plus spend. I can do a video on the details and implementation in Python of this. Tell me in the comments below if you want to. But you're trying to model the maximum potential exposure and the spend at half of that. And the relationship between your spend and your impressions will depend on the theoretical ceiling of exposures, because there will be no additional benefit beyond that, and you will have channel specific capacity. And some models you will the benefit of this is you can try to estimate these parameters, and the model will attempt to learn this relationship and then use this relationship to allow you to optimize. And now we come to the part where we need to select and calibrate an how do I know that the model will reflect reality? Now, there is the statistical parameters of a linear regression. So we're talking R squared, i.e. model fit. Also, we have R squared, which is a measure of model fit. It will tell you how much of the data's variability is explained by the model. You have RMSE, i.e. root mean squared error. It's basically the error between the forecasts of the model and the actual data. And after you have AIC and BIC. This is for model complexity because you can you can overfit a model. You can have too many parameters. So you need a way to penalize the model for that and to basically don't you need a way to balance complexity versus explainability. And if you're using a Bayesian model, then the conversion is important. I.e., are the distribution stable and are all of the Monte Carlo chains converging to a value? Then comes business validation. And this is a little bit of a business sense check. Does the model output make sense? Does it align with what you know of your market? Do you have reasonable ROAS distributions? Do you have sensible channel contributions? This is where subject matter experts are important. And this is where Bayesian models shine a little bit more because you can feed these validations back to the model by adjusting the priors. And then comes the experimental validation, i.e., testing the model itself. You can do live testing, you can do geo-based testing, and basically what we're talking here is you select the geography of your market and you decide to, for instance, stop specific campaigns or specific channels from specific geos, and you compare them with other geos, or lift analysis to understand how much lift is a channel giving you, or the simplest is a channel holdout test where you attempt to shut down an entire channel and see how much of your sales go down or not. Most of the times, you're not shutting down an entire channel. No marketing manager will allow an analytics manager to do that. So you need to combine some of these techniques. So, for instance, when you're sometimes doing channel holdout tests, you're shutting down channels, but you're shutting them down on specific geos, and you're comparing with other geos. And this is where difference in differences methods or synthetic control or geo-matched tests come. And also, the simplest is out of sample predictions. The past, you can train the model on the far past. You can train the model while living out the recent past, like last quarter. You train your media mix model and then you forecast it because you know what happened. And if the model is not accurate in this out of sample forecast, then you have a problem. You need to go back to the drawing board. And there's some best practices on experimentation, especially if you're doing tests. Ensure statistical power, and this is very common. People forget about this. Calculating power, i.e., what is the minimum detectable effect I can have from that test. You should consider long-term effect, and you should also account for seasonality. And then comes, we have the model works. Now we need to understand what is it good for? What are we going to use it? And the first and foremost, the main use of it is for budget allocation. It allows you to do optimal budget allocation. And you do this by optimizing with channel specific ROAS curves, i.e., the response curves per channel, the saturation points per channel, and then you're going to have cross channel interactions. And that's what the media mix model is trying to understand, how channels interact with one another and how channels interact with economic variables. And that also with, for instance, seasonal response variations, you then are going to maximize ROAS time spent, subject to the constraint of your total spend per channel needs to be less than or equal to your total budget. And you can also enforce a constraint of your spend per channel needs to be between a minimum and a maximum. But basically, this is linear programming. This is not the hard part. Once you have it validated, it basically tells you what the model is doing underneath. You're basically doing response curve fitting. You're estimating channel specific parameters. You're modeling the diminishing returns. You're accounting for ad stock effects, and you're including the saturation points and also on the cross channel interactions. And you have budget limits, you have channel constraints, you'll have business rules. For instance, you might have annual commitments on your budget. So you might have channels that you cannot move the budget towards the optimal level. Or a good rule of thumb is never let the suggest plus or minus 30% of a given channel. That's too much of an impact. And usually marketing managers and business managers feel that's way too much. So usually you try to compensate for that. And on the response curves part here, we should be careful with using response curves alone. So there's a temptation of, because this is one of the outputs of an, which is the response curve, of using that for budget allocation. Because the response curve tells you for that particular channel, it will tell you what is the return on investment for increasing another dollar of investment in that channel. So if you have a very steep response curve, for instance, that means that you're going to have incredible return on investment. If you have a very flat response curve, then that means adding another dollar will only give you a very low incremental value. Now, the problem with just using response curves is that you're missing a lot of the media mix model. Specifically, you are missing cross-channel effects and you're making an assumption. And the assumption is that every channel is independent from one another. And every marketer will tell you that is not the case. Channels will interact with one another. That's the point of a marketing strategy. So if we know, as people working in marketing, that channels interact with one another, be very careful about using response curves alone. You're missing the full model context. You're missing channel interactions. You're missing seasonal patterns. You're missing market conditions. You're missing external factors, consumer behavior, or economic conditions. You're missing a lot. There's the rule of thumb sometimes used that for channels with very short impacts, i.e., short ad stocks, you can do this. But again, be very careful because you are missing the channel interactions. You're missing how an investment, for instance, in above the line, or an investment in brand, or an investment on top of funnel will affect your paid search. Another way we can use is to do what if analysis. So basically, once you have a full model, you can use it to test assumptions. You can use it to understand what happens if I increase my spend on a specific channel, or what is the optimal spend to reach a specific target. So this basically means all models and most tools allow you to do budget changes for introducing a new channel, eliminate a channel, cut or increase your spend, shift timings, or reallocate your channel budgets. Another very good aspect in the what if analysis is to understand, and this is a bit of prescriptive analytics, can I reach a target? And if so, what's the mix? If management wants me to get 10 million more sales, can I do it? And if so, what should be the optimal media mix to get there? So most MMs are also very good and used in this what if analysis. I hope you've enjoyed the video. Leave me a comment down below if you want me to go more in depth in some of these topics. I will leave a link in the video description for this presentation. And if you're interested, much of this presentation was picked up from the chapter in my book about data analytics for marketing. So it's on Amazon if you want. I hope you come for more videos. Thank you.